Hello, I'm Harry Sanders. I'm a member of the geography team here at Canterbury Christ Church University, and you join me in my laboratory. And my laboratory is this. Now, granted, this British Lowland River doesn't exactly look as beautiful as a lot of other rivers that we see in the world, but looks aren't everything. I'm excited about British rivers because despite the fact that they take up less than 1% of the surface area of land, rivers globally make up more than 10% of all species on Earth. They are disproportionately biodiverse. But unfortunately, this biodiversity is under threat. So why are these rivers under threat? Well, they're under threat from a lot of different pressures. We can look at climate change, changing the flow regimes, so we're getting rain falling in more extreme and less frequent patterns. That's changing the way in which water comes down these watercourses. We've got dams that are blocking up the streams that are stopping the migration of fish and sediment and essentially putting a stop in the way of natural processes. But what I'm really interested in is habitat change. And one of the big habitat changes that I look at is fine sediment. Now, fine sediment is anything that is small, fine material like clays and silts that when they get washed down the stream they make the water murky. And this has really deleterious impacts for the organisms in the rivers. We can look at it directly affecting organisms such as fish by reducing their visibility and their ability to hunt, but we can also have a look at its effect on their food sources and where they can breed. Typically, if we have a look in lowland rivers such as this, we would expect there to be a bed of clean river gravels that look something like a cornflakes packet, where at the top of the packet you've got nice clean large chunks of cornflakes, our coarse gravels, and then as you go down to the bottom, that's where you find your fine dust, our sediment that is trapped underneath those gravels on the top of the river. However, if we have a look underneath the river here, what we find is that the river does not look like that. We get patches where those two have been mixed together. And where the invertebrates, which are our fish's food, live in that gravel matrix within the riverbed, unfortunately this fine sediment is blocking up all of the holes that they live in. It's stopping the water getting down into the riverbed, bringing nutrients and oxygen down to them, meaning that it's just not possible for them to live there. And the same goes for the fish eggs. The fish, such as salmon and trout, like to lay their eggs within the gravels where they're clean, they're going to get fresh oxygen brought down to them. But unfortunately, when we clog those spaces up with fine sediment and the water can't flow, it's just not viable for these fish that we value very high culturally to be able to breed and maintain a natural stock. So, how does all of this excess fine sediment get into these rivers? And why has it happened over such a short period of time? Well, partly humans are to blame. As we increase our numbers on the planet, we have a greater agricultural need to drive for food, then we're going to increase the number and the size of our farms, and rain washing all of that fertile soil off of the tops of our agricultural fields into rivers is partly to blame. Also partly to blame are our urbanised surfaces. The more roads, the more pavements that we have, the easier it's going to be for any of our soils to get washed straight down into our river systems. But humans are not the only animals to blame. Whilst we typically think of habitats driving species distributions, my research looks at it the other way around. How do animals change the habitats and change the geophysical processes around them? Now, a really common example with this would be beavers and beaver dams, of how a beaver will cut down logs of trees and use them to construct a dam in a river to be able to slow the flow behind it to create a deeper section of water for them to live. And not only does that change the ecological surrounding in creating a home for the beavers, that's going to change the flow of the river and therefore the change in sediment transport that comes with it. And whilst we think of this with beavers, really all animals are doing it. Penguins will build rock nests. We can look at fish such as salmon constructing redds, digging gravels out in the rivers to lay their eggs. And pretty much all invertebrates that we look at under the water, even through their small movements, they're going to make a change to these geophysical processes in rivers. Now, when we think of these processes though, they've all been going on for thousands of years, so why the sudden change? And that's because not all species in these rivers have been here for quite so long. Whilst the composition of ecological communities naturally changes over time through species expanding their range into new habitats, humans have accelerated these processes and have directly introduced new species that would otherwise not have been able to naturally colonise. Whilst freshwaters are exceptionally biodiverse, they are also disproportionately affected by invasive species, such as the Chinese mitten crab, which carries crayfish plague fatal to white-clawed crayfish, zebra mussels, which change the nutrient dynamics of ecosystems through their efficient filter feeding as well as directly growing on native mussels, and signal crayfish, which are effective predators of native invertebrates and fish eggs. However, it's a novel behaviour displayed by the signal crayfish that I've been particularly keen to study. In the UK, in some rivers where they've invaded, signal crayfish have constructed burrows into riverbanks, directly supplying large quantities of fine sediment into invaded rivers. But not only are these burrows supplying sediment into the river directly by themselves, the burrows are making the riverbanks weaker, which make them easier to collapse and easier for the river to erode the sediment away in high flood events. So what we've spent the last few years doing is monitoring riverbanks around the country where signal crayfish have burrowed by taking a small length of rod, something we call an erosion pin, inserting it into the bank, and then what we can do is we can measure the amount of rod that is still left exposed outside of the bank, and that will tell us how fast the bank has eroded. What that's been telling us is that at some sites where signal crayfish are constructing their burrows, not only are they supplying sediment to the river directly from their burrows, but they're accelerating the bank retreat. And for every kilometre of river, we're finding that signal crayfish are recruiting around about 25 tonnes of excess fine sediment into these river channels every year. However, I've come to this river to investigate a very different invasive species. Here, invasive quagga mussels are present in very high population densities, up to 500 per square metre, covering the riverbed with potentially an opposite effect on river sediment dynamics to the signal crayfish. Now, this is a quagga mussel, and what you can probably see is that when I picked it up off the riverbed, I've not only picked up the mussel, but I've picked up a load of gravel that its byssal threads have attached itself to. Now, these originate from the Ponto-Caspian region in Russia and Ukraine, and global shipping has brought these around the world. They're quite famously in the Great Lakes of the North America, but now they're also in the UK. And I'm in the Thames catchment here. The River Thames, a big shipping port, is a meltdown of invasive species. It's a melting pot of all of the worst invasive species that we see across the world, and the quagga mussel is no exception. But what I'm really interested in is the fact that these mussels, through their byssal threads, whilst they have ecological effects, I'm interested in their geomorphological effects. How might these mussels attaching themselves to the riverbed gravels and essentially tying it together change the physical processes that we're seeing in these rivers? So what I'm in the river doing today is I'm here characterising the riverbed. I'm asking, what's the size of the gravel? How many of these quagga mussels are there? How much sediment do they attach themselves to? Because we're going to reconstruct this riverbed in our laboratory in an artificial river. And what that allows us to do is it allows us to increase the flow velocity, increase the depth to simulate a flood event, which is when most of these gravels would normally be moved. And whilst our signal crayfish destabilised the river banks and recruited extra sediment into the river, these quagga mussels may have a stabilising effect, and they may anchor down the gravels, anchor down the sediment, and stop it moving during a flood event. And this sediment not only has impacts for ecology, but it also has direct impacts for humans. I'm at this river specifically because about 2 kilometres that way is the village of Raisbury, which is a village on the banks of the River Thames. And it's kind of locally famed around here for being flooded every time a large storm comes through during the winter season. Now, there are many reasons for why Raisbury in particular gets flooded, partly due to the shape of the River Thames catchment. But one of the reasons that the locals around here attribute the flooding towards is sediment in the river. When you get a build-up of fine sediment in the channel, it reduces the capacity of the channel, giving the water less space, meaning it flows over bank and floods an area much more easily. Now, recently, there's a lot more sediment been coming into the river, and invasive species, how they're going to behave, what effects they're going to have as they increase their range throughout this River Thames catchment is a really key question that the people of Raisbury are going to want answers to. And so understanding what effects they're going to have not only on the local ecology, but the sediment dynamics of rivers such as this that feed into the River Thames around villages that are prone to flooding, such as Wraysbury, is really important for us to be able to understand how these rivers function regarding their biodiversity, but also more holistically as ecosystems and how their impacts are going to affect us directly as humans.